Okay, so last time we had said that there are enough large primes for us to have a pretty good chance of picking one at random. So if you're looking for a prime that's about the same size as, you're looking for a prime that's 1024 bits long, you can find one because for numbers that are this big, approximately one in every 1 in every 1,000 numbers is prime. So assuming that you can do a quick primality test, you can find enough. There are enough prime numbers that RSA will work. And then we asked, well, how do you prove that a number is prime? And there are some deterministic primality tests that give you a definite yes or no that's definitely right, but they tend to be kind of slow. And there were none known at all until like 15 years ago. And we've been using RSA since the 70s. So we were able to find the large primes even before we had the deterministic algorithm. And we kind of we presented Fermat's test. So if you have some number n and you want to decide whether or not it's prime, one thing you can do is randomly select some number in z mod n. So just select some number between 1 and n minus 1. I guess there should be a star here because you actually don't want to pick 0. Anyway, yeah, just pick some non-zero number. Now I regret doing that star. If n is composite and you don't know how to factor it, you really have no idea what zn star is anyway. So you just ask yourself, is it true that a to the n minus 1 is congruent to 1 mod n? And so you know that this will definitely be yes if n is prime, and if n is composite, it will probably be no. So just checking whether 2 to the n minus 1 is congruent to 1 or not almost always works. I mean, it's not good enough for like cryptographic applications. I'm just saying that if you're like doing like some trivia with your friends or something, and you want to know if n equals, I don't know, 57 is prime or not, and then if you do what is 2 to the 56 mod 57 equal, let's actually see what it's equal to mod 57, and it will almost certainly not be equal to 1. So let me come here and we'll do, so what is 2 to the 56 power mod 57 is 4, and that means 57 is composite. And so this is 4, and so 57 is not prime. Okay, and so that's the basic idea for, well, that is the entire idea for the Fermat primality test. The problem with the Fermat primality test is that there are some weird numbers called Carmichael numbers, which have not that many numbers that reveal the composite nature of the number. So we looked at the Wikipedia article on Carmichael numbers last time. The smallest one is 561. So if you take some number, actually let's, so if I pick any a and z561 star, so then here I definitely mean the star. And then if I do a to the 560, this is always going to be congruent to 1 mod 561. So it's like every possible a almost is a bad choice. If you factor 561, let's do that here. Come back here and do this. So factor 561. It's 3 times 11 times 17. Oops, where are we? Okay, so this is 3 times 11 times 17. So in order to actually be in the multiplicative group, I need to pick some number that is relatively prime to 561. So an example would be 13, right? So let's say that I pick a equals 13. And then I do, what is 13 to the 560, mod 561? Let's come back to the terminal window and do that. So what is 13 to the 560 mod 561? It's 1. And that happens for every number in the multiplicative ring mod 561. Sorry, multiplicative group mod 561. But if you pick some number that is not relatively prime to 561, it won't necessarily work. So there is some chance that the Fermat test will reveal the truth. For example, 12 has a factor of 3, and so does 561. So if you raise 12 to the 560th power mod 561, you get 375. And so you can tell that it's composite using this Fermat trick. It's just that nothing in the multiplicative group will ever reveal it. And that's what a Carmichael number is. So this makes people uncomfortable enough that that they want some other better test, and there's a better test that's based on a similar idea, and this is called the Miller Rabin test. And now we're gonna talk about how the Miller Rabin test works. So the Wikipedia article on the Miller Rabin test is excellent. It's much better than our book. Our book makes a number of terrible mistakes. If you look at the error errata for our textbook, you'll see that the algorithm is wrong and a couple of other things are wrong. It's very confusing. So rather than reading our textbook on this one, I really suggest that you just read the Wikipedia page. Okay, so this is based on, so if n is prime and a squared is congruent to 1 mod n, then a equals 1 or a equals minus 1. So this is a fact about prime numbers. So this is something that's true for all primes, and something that's usually not true for composites for choices of a. So let's prove that this is true. So if n is prime and a squared is equal to 1 mod n, then a is equal to 1, or I should say congruent to 1, or congruent to minus 1 mod n. So let's prove that it's true. So suppose that a squared is congruent to 1 mod n. Then you get a plus, oh sorry, I'm gonna skip I don't want to skip a step. So let's pull the 1 over here and we get a squared minus 1 is congruent to 0 mod n. Okay, and now I can do difference of squares here to factor this into a minus 1, a plus 1 is congruent to 0 mod n. And so what is this saying? This is saying that n divides a product of these two numbers. So n divides a minus 1 times a plus 1. But n is supposed to be a prime. So the only, if a prime divides a product, then it must be a prime factor of one of the two parts. So either n divides this or n divides that. So suppose that we're in the case where n divides a minus 1. Then that means a minus 1 is congruent to 0, and that means that a is congruent to 1. Okay, so that's one possibility, is that a is congruent to 1. So suppose this other possibility is true, that n divides a plus 1. So in that case, a plus 1 is congruent to 0 mod n, and then a is congruent to minus 1. And so we've proven the fact. So if n is prime and a is a square root of 1, then either a is positive 1 or negative 1. So there are no non-trivial square roots of 1 when n is prime. Okay. So this this observation here, or whatever you want to call it, is it sort of busts the Carmichael number wide open. So let's pick some number that that's in here, 7,561 star. So here's the factorization of 561. We know that the elements inside Z561 star are just the numbers that are relatively prime to 561. So one number like that is 7. And so we know that 7 to the 560 is going to be congruent to 1 mod 561, because 561 is a Carmichael number, and that's what happens. But we can ask the question, well, how did it get to be 1? If you look at this exponent 560, let me actually come back over here to this terminal. So factor 560. So 560 is 2 to the 4th power times 5 times 7. So now let me take that back to the other sheet here. Okay. So 560 is equal to 2 to the 4th times 5 times 7. And of course, 5 times 7 is 35. Okay. So I can take, let me take 7 to the 35th power here. All right. And so I've taken the odd part out here of 560. And now I can start, if I square this, so if I square that 7 to the 35 squared, this is equal to 7 to the 2 times 35. And then if I were to square that, I would get 7 to the 4 times 35. And if I were to square that, then I would get 7 to the 8 times 35. And if I were to square that, I would get 7 to the 16 times 35. Okay, so every step here, what we're doing is squaring. So square, square, square as we go along here. Okay, and we know that in the very last place, this is congruent to 1 because 16 times 35 is just the same thing as 560. So we know we have a 1 down here. So how did we get to that 1? So like what are these other things, for example? So I figured these out before class. So this one turns out to be 7 to the 35th power is congruent to 241 mod 560. Everything is mod, sorry, 561. And this one is congruent to 298. And this one is congruent to 166. And this one is congruent to 67. Okay, now this proves that 561 is composite. Why does it prove that? The reason it proves it is because we squared 67 and got 1. Look, to get from 67 to 1, we squared. So that means 67 squared is congruent to 1 mod 561. But we said that this never happens for a prime. So for a prime, if something is a square root of 1, the only way that can happen is that it's plus or minus 1. So this step here would be impossible for a prime. So a prime could never do this. So since a prime could never do that, 561 can't be prime. So this is not possible. And so we've kind of just busted 560 being composite. And so 561 is composite. So this basic idea is the Miller Rabin test. So once you kind of understand it, understand that part of it, then the rest is easy. The actual algorithm looks kind of complicated, but you just have to remember what Miller Rabin is basically doing is it's trying to catch some number becoming 1 when you square it when it's not -1. Okay. So should we, I don't know, I could phrase it kind of more generally here. Maybe just do a different page. So let's do Miller Rabin outline. Okay. So n is some number, and you want to decide whether n is composite or prime. Many times, I'll say more about this later, you just pick some a at random. So I put this little r here to say uniformly at random. So just pick some number in Zn. Of course, you know, it's not helpful to pick like 0 or 1 or -1 or something like that, but pick some a. So we're gonna, it's still based around this Fermat idea. You know, the Fermat idea is a to the n minus 1 must be congruent to the 1 mod n. So maybe that's true, and maybe it's not true. Let's assume that it is true. What Miller Rabin is concerned with is how do we get to 1? So we want to just first we factor n minus 1 into a bunch of 2's. So it's some odd number r times 2 to the k. That's what we did with 561. So this r here is odd. And now you raise a to the odd power r. And so what is that? So if a to the r is congruent to 1, or a to the r is congruent to -1, then the test is inconclusive for r. Oh, sorry, inconclusive for a. Okay, and at that stage you would come back here and you would select another a. So you're trying over and over again to try to find somebody that will sort of like spill the beans on n and reveal that it's composite. And it turns out people have proved, so an a like this that doesn't reveal the truth, that gives an inconclusive result, that's at most a quarter of the numbers in here. So you have to be pretty unlucky to get an a that does this. This kind of a is called a liar. So this is something that might happen, and if it does, then you just pick another a. Otherwise, so come back here to a to the r, okay. So once you have a to the r, and so this is congruent to something other than plus or minus 1, you can start repeatedly squaring it. So you produce a to the r, a to the 2r, a to the 2 squared r, a to the 2 cubed r, and you keep doing this, and eventually you're going to get down to a to the 2kr. And so remember that this is the same thing as just a to the n minus 1. So presumably this is congruent to 1. If it's not congruent to 1, then we already know that n is composite anyway, because it fails Fermat's little theorem. So along the way here, there's going to be some first place where it starts becoming 1. You know, once it becomes 1, it's one ever after, because if you square 1, then 1 squared is 1, and all we're doing on this sequence is repeatedly squaring. So there's some first place where 1 occurs, and maybe it's the very last place. So the question is, what happens before the first place that 1 occurs? So if n really is prime, what's the only value that could go right here if n is prime? We're going to square this number and get 1. So what's the only thing it could be?
1?
It could be 1, but we're assuming that this is the first place that 1 shows up on the list. So there's some first place where 1 shows up. And so what is the thing that comes right before the first 1? What's the only thing it could be? What is the special thing about primes? The special thing about primes is that if you square a number and it's 1, then it's either 1 or minus 1. We're saying that it's not 1 because we're saying this is the first time that 1 showed up on the list. So that means that if n is prime, then this must be minus 1. And if it's not minus 1, then the number is composite. And so when that happens, A is called a witness. And so 3/4 of all the A's in Zn are witnesses, and only 1/4 are liars. So let's say n is some ridiculously large number, like it's like 2 to the 2048 or something like that. So you can pick as many A's as you want. So let's say that we pick 100 A's at random. Then what are the chances that you get 100 liars? The chances that so there's a 1/4 chance that the first one is a liar. And then independently, there's a 1/4 chance that the second one is a liar, and so on and so forth. So if you pick 100 A's at random, the chances that you get 100 liars is 1/4 to the 100th power, which is 1/2 to the 200, which is basically 0.
It's a very small number.
Yeah, very, 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 very small number. So if you just do this process with 100 randomly chosen A's, then if you don't catch the number being composite, then it's almost certainly prime. There's a chance that you're saying that it's prime when it's actually not. There's a 1 and there's a 1/infinity chance that that's true. If you say that it's composite, then it definitely is composite, because you only say that when you bust it being composite. So there are no false negatives, but there could be a false positive. But the chances that you have a false positive is like 1/2 to the 200th power. And it could be made even smaller. The number of times you try is the security parameter, which we'll call S. So this is what would happen with a security level of 100. And if you wanted to, you could make the security level even higher. It just depends on how long you want to wait. So the higher you make the security level, the longer you have to wait for the primality test to complete. And there's a fairly serious software library called Maple. This is discussed on the Wikipedia page, and Maple is installed on every CUNY computer, or at least it used to be. I think it's a waste of money, but anyway, I think it's there. And there are some numbers that Maple has this function is prime. And what is prime actually does is it does the Miller Rabin test for a certain few numbers. I think it does 5, 7, 5, 2, 5, 7, 11, or something like that. And then if none of these are witnesses, then it just says that the number is prime. But it turns out that that is not really sufficiently reliable, and you can trick Maple, which of course pleases people. But this is another reason for picking the A's that you choose. You want to pick them completely at random. People have found numbers that are not prime, that have no witnesses, like in the first 300 choices or something. So you want to be sure to pick the A's that might be witnesses at random. And
Can I ask you a question
yeah.
real quick?
Uh-huh.
So this is in general, like to find like prime numbers and figure out what is prime and what isn't prime.
Yes.
And like Fermat's theorem also kind of does that. So
Mm-hmm.
why would you pick one over the other, like in a specific case?
Yeah, this one will work whenever Fermat's little theorem works, because it's based on the fact that, you know, a to the n minus 1, you know, is 1. So it does check that. But then it will also, but there are things that can fool the Fermat test. Like the Carmichael number had a lot of liars. So, you know, every A in Z561 star was basically a liar in the sense that it said that A to the 560 was congruent to 1. So every A in this set failed to be a witness to the compositeness of 561, except for a few that have a factor in common with 560, that have a factor in common with 561. So in this situation, most of the elements here are liars for the Fermat test. But with the Miller Rabin test, most things are witnesses. So with 561, you have like a huge number of Fermat liars. That's like the big, with a Carmichael number, that's going to be the big preponderance here, and you only have a few witnesses. So you're hoping that if you pick a bunch of things at random, you'll find one witness. All you need is one witness. But when you do the Miller Rabin test, it's sort of the reverse. So almost everything, well, 75% at least, is a witness. And at most 25% are liars. So if you randomly select a lot of things in the Miller Rabin test, then you're almost certainly going to find a witness, because almost every, 75% of things are a witness. So if you just choose, even 15 of these at random, the chances that they're all liars is like basically 0. It's like 1 in a billion chance.
So
So
if
that's,
you really wanted to be sure, like you would do all of them and then kind of compare your results?
yeah, but
Do you do that?
you could do that in theory, but to do that you need like a compute, that like Dyson sphere kind of alien computer. So with
Okay.
a real computer, there's like, you'd have to try this many times. But what you could do is do one of the new deterministic primality tests. I've never seen code for one of those. I don't know if anybody's coded one of those up or if they're just theoretical, but there are polynomial time primality tests, but I think they're pretty slow. Wikipedia said there was one that runs in time, like big O with a tilde over it, like n cubed or something, where n is the number of bits. So n would be 2048. So if that's true, then
It's
you
still
could,
very, very big.
yeah, then you still have 2000 cubed. And so the Miller Rabin test is still going to be faster, and it's almost as good. And do you guys know what the little tilde means on top of the big O notation?
I forget.
It means ignoring logarithmic factors. I never learned that, but I've just like I don't know. Now I know it. Now you know it too. So let's look at I coded up the Miller Rabin test on CodeCalc, and I think I passed it out to everybody. So let's go. It's in activities, primality testing, and here. So there it is at the bottom there. You can kind of walk your way through here, like let n be 561, then you need to write some code that that basically divides out all the 2's. So this function here just divides out all of the 2's. This double slash here means integer division. And this is the odd part. So as we go through here, we just keep dividing out 2's, and then we record how many we've seen, and keep going until n odd really is an odd number. And so in the case of 561, we know that there are 4 2's that come out. And let's make A 7. This is just the same example that we did on paper. So first you take A and you raise it to the odd part, mod n, and then you ask yourself, is it true that it's equal to plus or minus 1? And the answer in this case turns out to be false. And so you just, now you repeatedly square. So b is equal to b squared mod n, and then I'm printing it and whether or not it's equal to n minus 1. And every time I subtract 1 from the number of 2's. So these are the same numbers that we got before. So this is what we have to write the algorithm to detect is you square 67 and get 1. That's not supposed to happen, because if you square something and get 1, then the thing that preceded it is supposed to be minus 1 if it's a prime. So here's my code for the Miller Rabin. So return true if n is probably prime. You can pass in s as a security level, and return false if n is composite. So the way these algorithms actually work is it turns out to be a lot faster. First, just to check if it has some small factor. And so that's what this does. So you can just write down a list of like the first 10,000 primes or something. Most numbers that are composite, even big ones, have some small prime factor. And it's really fast to check those, check whether it's divisible by some small prime or not. So usually that's the first part of Miller Rabin, just because it is a big speed up. So if it has a small factor, then you just return that it's composite. And now you have to do this thing where you divide out all the 2's, and then you report back how many 2's there are, and then give the odd part 2. And then, so this while loop is going to be choosing a bunch of A's at random, and the security level S is just the number of A's to try. So let A be a random number here. The way this random function works, it could possibly return n minus 1. So it's some number between 1 and n minus 1, including n minus 1. That's unusual for Python, that the right endpoint could be included, but that's the way they wrote it. So now you get B, which is A to the odd power. And if that turns out to be 1 or minus 1, notice that this is how you express minus 1. Then it's inconclusive. So a prime might do that. So A is either the number is prime or A is a liar. And now you go and you do the repeated squaring part. So square what you have, and if it's equal to minus 1, then the test is inconclusive, because that's what a prime would do. So when we get to this line, we know that that we haven't seen any minus 1's. So in this case, 1 just popped out of nowhere. So in that case, we know that n is composite, because that's what a prime number would never do, is have a square root of 1. Okay, so now we get done with all of that stuff. Notice that we left 1, 2 at the end. So we checked all the 2's that we had. We squared it all those times, but we kept 1 in reserve, so there's 1 left. So we know that if we were to do that and the thing were prime, then we would get 1. And so if it is prime, we know that that it has to be minus 1 now. Otherwise, it's composite. So if it's not minus 1 here, then it must be composite. But if it makes it through all of those tests, then you return true. You know, we never caught it. We never caught it being composite, so we give it the benefit of the doubt now after we've tested it all those times. so here it is, like actually working. I wrote this little line of code here just to compare it against the Sage is prime function for 10,000 randomly chosen numbers, and so it seems to work. And now you pick a random integer between 1 and 2 to the 2048. So this n is enormously big. And if Miller Rabin says it's true, then you print it out. And this runs pretty quickly. I'll enter this, and then we can see how long this takes. Sometimes CoCalc takes a long old time. Let's see if this thing is done. Yeah, that's done. Oh, and there it is. Okay. So you can see it doesn't take that long, but it does take a while. And that is why generating parameters on for SSH, like let's come back here. We just do like SSH key gen. This can take quite a while. So it didn't take that long. Is there, does anybody know how to tell it how many bits you want the thing to be? Oh, that -b is the number of bits. So let's tell it that we want 4,096 bits. Oops. Crap, it did it pretty fast. Well, that's disappointing. But it is even that, you know, any kind of noticeable lag is fairly slow, and this can take a long time. Let me see here. I'm going to put it all the way up to 16,000. Okay, now it's chugging. And notice how much faster this code ran than my stupid CoCalc program. So it was able to find a 4,096-bit prime pretty much instantly, or actually two of them. But my thing took like 10 or 20 seconds or something. Okay, I'm satisfied that you know. So as the number of bits goes up, it starts to significantly slow down. So let's come back to just general RSA stuff. So we're going to leave the number theory aside for a second and just talk about some practical issues with RSA. And so one problem with RSA is something called malleability. You know, like and just the meaning of the word malleability just in ordinary English means bendable. And this can be a bad or a good thing for a cipher. What it means is you can change the ciphertext in such a way that you get a predictable change in the plain text. For example, in RSA, you can double the plain text by changing the ciphertext in a certain way. So in the plain text. So here's an example. Let's say that Alice and Bob are communicating using RSA. So, you know, Bob sends Alice his public key, which is n in the public exponent. Then Alice creates some message, who knows what it is, and she encrypts it. So y is equal to x to the e mod n. And now Alice starts to send y back to Bob, but oh no, there is somebody in the middle. So you can call this person whoever, Eve or Mallory. I kind of like Mallory better because Eve suggests eavesdropper, which kind of suggests passivity, that it's passive attack. I'll call this Mallory for malicious actor. Also, this is malleability. So Mallory can stop y, and then she replaces it with a new y, call it y prime or something. So y prime is s to the e times the old y. where S is something that Mallory chose, like maybe 2 or something. And then Mallory sends Y prime onto Bob here. And then Bob proceeds to decrypt Y prime. And what does he get? He gets some value X prime, which is Y prime to the D mod N. And so what is, I guess this should be congruence. And what is that? That's S to the E Y to the D, which is S to the E X to the E to the Dth power. So this becomes S to the ED times X to the ED mod N. But remember, the magic thing about RSA is that anything to the ED power is 1. Or sorry, no, it's just the original thing. So this is S times X. So now Bob has this thing that he thinks is the decrypt, but it's not the decrypt of the X that Alice sent, it's the decrypt of twice X. And so if X is like the amount of money that Bob is supposed to pay Alice or something, like Mallory has just multiplied it by a factor of 2, and there's no way that that Bob can know the difference. And in reality, there would be some kind of authentication thing also happening, but this is an issue. Malleability can be a good thing because it means that you can have somebody do computations on a value that's encrypted, and they can do like productive real computations using the ciphertext without ever being able to know what the ciphertext actually is. So like in cryptocurrency, there's some privacy coins that rely on malleability, and it would be, I don't think anybody's really gotten this to work, but you could imagine like an encrypted database server or something where you just have it's still usable, but the machine that's hosting the database never gets to see the actual values that it's manipulating. So that is that's a problem with RSA. Another problem with RSA is that the way we've described it above, it has deterministic encryption, which we've said several times is bad. So if you encrypt the same value twice, X to the E is the same thing as X to the E. So if you encrypt the same plain text twice, you get the same ciphertext both times. So that's deterministic encryption, and it's bad because anybody who's observing you can see if you are sending the same message repeatedly, and they can use statistics to figure out what it is you might be talking about. There's another kind of like minor problem called the small message problem. So if you pick if you pick some fairly small message, like let's say you pick the message 3 or something, and then it happens that the public exponent is also some small number like 7, then when you compute the ciphertext, the ciphertext is just 3 to the 7th mod n. But this is also just 3 to the 7th. And E is public, so Mallory or whoever can take Y and just take the 7th root of Y, which anybody can do with a pocket calculator. And then what comes out is X. So there's something that stops all of these problems that we've just been outlining, and it's called padding. And padding is just running before you encrypt X, you run it through a little bit of a, it's almost like a cipher, except it doesn't have a key. It kind of scrambles things around. And the one that people often use is called optimal asymmetric encryption padding. So this is asymmetric. People also often call public key cryptography asymmetric keys, just a synonym for the same thing. So this is optimal asymmetric encryption padding. And let's go look at the Wikipedia page because they have a nice graphic. Optimal asymmetric encryption padding. Oops, and I put a little slash there. Okay. So you can read through this. I just wanted to show you this picture. So these this G and this H are hash functions. I don't think we've said too much about hash functions, but hash functions they scramble things and also adjust the length, and they're very sensitive to the bits that go in. So, you know, if one bit of R here were to change, then this output would be completely different. And then if one bit of this were to change, then this output would be completely different. So you can think of G and H as being hash functions. R here is a nonce. It's a randomly chosen number. And by choosing R at random, you get probabilistic encryption. So this gets rid of the deterministic encryption problem. So this M here is the message, and R is also a fixed size, and this entire input has to be a fixed size. So you might have to pad the message with zeros to make all the stuff be, you know, however long it has to be. And then you run it through this process, and notice that this process is a lot like a Feistel cipher. So you're running, you know, the right side goes through some kind of transformation, and then it turns out in this case, it also does it the other way. But this still has the good property that a Feistel cipher has, which is if you do this backwards, it undoes itself. So imagine what would happen here if you just sort of turn these wires around. Then you put X back up through here, it comes through here again, and it XORs with Y, but that undoes what it did the first time. So that undoes this first step. And then, so this is now this is R on this wire. R goes through here again and hits whatever this is and undoes what this did on the way down. And so if you do this forwards, you get these two things, but if you do it backwards, you get the original message back. So what comes out down here is the OAEP padded message. And then you apply RSA to that, and it doesn't have any of the problems that we outlined earlier. So that is, that's padding. So what else have we got? So we just finished chapter, whatever chapter that was. I think it was chapter 6, or maybe it was chapter 7. And it's time for us to go on to the next topic. Anybody have any questions to say goodbye to RSA? Okay, goodbye RSA. Still have to know about RSA, of course. So we're going on to the next chapter. So why is it a new chapter? The previous chapter that we did was RSA. And RSA was basically, it was public key cryptography, and it was based on a hard problem, and that hard problem was integer factorization. So this next chapter is also about public key cryptography, but it's about public key cryptography that's based on a different hard problem, and that hard problem is the discrete logarithm problem. So just to remind you what the discrete log problem is, let's say that I give you 2 and I give you, actually let me change this. Let's say I give you 3 and I also tell you 7. So here we're going to be working in Z7 star, okay? So it turns out that that this element 3 can generate every element of Z7 star. So Z7 star is 1, 2, 3, 4, 5, 6. So look at what happens if I just do powers of 3. So I start with 3. Maybe we should keep track of the powers here. So this, you know, 3 to the first power is 3. If you square 3, you get 9, but mod 7, this is the same thing as 2. And then if you if you raise 3 to the third power, then 3 times 2 is 6. And now if you raise 3 to the fourth power, 3 times 6 is 18. But modulo 7, 18, so this is 18, but modulo 7, 18 is 4. And now if you raise it to another power, you raise it to the fifth power, then there's another 3 here, so 3 times 4 is 12. But mod 7, 12 is 5. And then finally you raise it to the sixth power, and 3 times 5 is 15, but 15 is 1. So look at what you've done here. You've generated every single element of the group. Hello, baby. So every single number in the group is some power of 3. And notice that they come in kind of a pseudo-random order. So that's actually good. That's one of the things that makes the discrete logarithm problem hard.
How do you draw?
So the discrete logarithm problem is, suppose that I just give you some number 4, and I tell you that 4 is some power of 3. So 4 is 3 to the x, or some unknown x mod 7. What you have to do is tell me what x is. So solving that is the discrete logarithm problem. And it has that name because what you kind of like to do is take log base 3 of both sides, because that would be x. But because of the mod 7, it's not like you can actually do that with like the real valued logarithm function that you learned about in calculus. It won't work for that. And you can use this notation in the discrete setting, but then how do you actually, you've just used notation. How do you actually compute that value? So computing that value is hard. It's not quite as hard as just like brute force. You can do it quite a bit faster than brute force. It's kind of like integer factorization. It's harder than polynomial time, but easier than exponential time. But it takes a good long old time to find out what that exponent was, and that's the discrete logarithm problem. So situations like this, like the one that we just described, these are called cyclic groups. So a cyclic group is a group that's generated by just one element. So what we just saw is that Z7 star is generated by 3. So 3 is a generator. The generating element is sometimes called a primitive element, or sometimes called a generator. I always say generator. And it's not the case that just any element of Z7 star is a generator. So remember the elements here are 1, 2, 3, 4, 5, 6. So some of these will be generators and others will not be generators. Like obviously 1 is not a generator. If you raise 1 to repeatedly, to higher and higher powers, so 1 squared is 1, 1 cubed is 1. So you're never going to get anywhere with 1. And do you remember this term that we've used before, order? So the order of a group element is the smallest positive power you raise it to, so that it's equal to 1. So the order of 1 is just 1. So let's try it again with 2. So with 2, you have 2 to the first power is 2. Then what do you get if you square 2? You get 4. And what do you get if you multiply 4 times another 2? So this would be 2 to the third power. The 2 to the third power would be 8, but 8 is 1. The order of 2 turns out to be 1. Sorry, 3. That's because 2 cubed is 1. So this is 2 to the first power. this is 2 to the second power, and this is 2 cubed. So the exponent that makes the 1 show up is the order. So the order of 2 is 1. And if we kept raising it to higher and higher powers, we would just go back to 2, and then we would go to 4, and then we would go to 1, and then when we multiplied 2 again, we would go back to 2. So this is like we're stuck in a little cycle here. And that's fine, it's just that the cycle doesn't get us all the way through the group. So we already know what happens with 3. So with 3, you get 3, then 2, then 6, then 4, then 5, and then you get 1. And then this would cycle back around too if you kept multiplying in 3s. The order of 3 is equal to 6, which is also the cardinality of the group. And that's what makes it a cyclic group. So another way to define a cyclic group is just a group where some element has the order of the group as its multiplicative order, or as its order. So with you can do the same thing with 4. So with 4, you get 4 and 2 and 1, because 4 squared is 16, which is 2, and then 4 cubed is 8, which is 1. All right. And with 5, 5 is another generator. You get 5, 4, 6, 2, 3, 1. So the order of 5 would be 6. So it is also a generator or a primitive element. And I forgot to write this before, but the order of 4 is 3. And now you've got 6. So, 6 is 6, but 6 is also congruent to -1. So what is the multiplicative order of -1? Well, -1 times -1 is 1. So that's true in modular numbers also. So you just get 6, and then -1 times -1 is 1, so you get 1. You can check that too, right? 6 times 6 is 36, which is 1 mod 7. So the last n-1 is always going to have order 2 here. Okay, so notice something, that there are 6 elements in this group. So the cardinality of the group is 6, and every single number here divides 6, and that always happens. That's called Lagrange's theorem. It's pretty similar to Fermat's little theorem and Euler's theorem. It's Euler's generalization, of Fermat's little theorem, which we've already talked about. And so here's so 1 divides 6, 3 divides 6, 6 divides 6. In fact, every divisor of 6 shows up once. Not only does every divisor of 6 show up once, but here the order 3 gave us this group. This it's sort of a subgroup, because it's its own cycle. So these are all just powers of 2. So a power of 2 times a power of 2 is still going to be a power of 2. So if I do 2 to the k times 2 to the l, this is just 2 to the k plus l. So you get stuck in here multiplying powers of 2 and getting other powers of 2. This is an example of something called a subgroup. So this subgroup has 3 elements, and it's the only subgroup that has three elements. So this other place where we had something of order 3, we ended up getting exactly the same elements, just in different order. So these are actually the same subgroups. Also, when order 6 came out, we of course always got the exact same subgroup, which is also the entire group in those cases. And the other ones were unique. So there's only one subgroup of order 1, obviously, and there's only one subgroup of order 2, and those were generated by plus and minus 1 and no other elements. Okay, so some of those things are always true, and we need to learn a little bit more before I need to actually write down the definitions and stuff, but this is a good preview. So a cyclic group is a group that's generated just by one element, and that is an element that has order equal to the cardinality of the group. And we also saw the cyclic subgroup theorem applying here, which says for every divisor of the cardinality of the cyclic subgroup, there's a unique cyclic. For every divisor of the order of the cyclic group, there's a unique cyclic subgroup of that order. Okay, so we kind of skipped way ahead there. So I was gonna prove that the order of every element divides the order of the group, but the textbook doesn't do that, maybe wisely, and I feel like I just hurt everybody's brain. So instead of doing that, let me introduce Diffie Hellman Key Exchange. So Diffie Hellman Key Exchange was invented in the 70s, I think, by Diffie and Hellman. And Diffie and Hellman are legendary cryptographers who have been around for a very long time. This was the first public key algorithm that had real practical applications, and it's still a crucial piece of cryptographic technology even today. And it does something which sounds unbelievable. So if I just pick somebody in class like Catherine, so suppose that Catherine and I want to agree on a cryptographic key, but we don't have an encrypted channel of communication already. We have to establish the key over a public communication channel like this one. So this is kind of the situation that you're in whenever you want to make an HTTPS connection with a website. You want to start communicating using encryption, but you don't already have an encrypted communication channel that you could use to do key exchange. So how do you establish a key without announcing your key to the entire world? But Diffie-Hellman Key Exchange is one way to do this. And if Catherine and I were to do this, then she and I could just talk, and after a couple of minutes, I would know a cryptographic key, and Catherine would know a cryptographic key, and nobody else, all of you people who are listening, wouldn't know the key. And so if somebody just told, this is like, magician stuff, like if somebody just told you they were going to do that, they would say, I would say that's impossible, but it's not impossible. And this is how you do it. So you have to agree on some parameters. So G is going to be a generator of ZP star for a big prime P. P is a large prime. And it turns out that there always is a generator for ZP star. So when P is prime, this is always a cyclic group. So there's some generator. In fact, most numbers are generator. No, well, okay. The number of generators is phi of P minus 1. So depending on how you choose P, that can be a very big number, in which case you can make it be the case that there are many generators, which is usually good. We'll talk about that more later. Sorry, my neighbor is mowing his lawn. Okay, so here's Alice and here's Bob. And Alice and Bob want to agree on a cryptographic key in the presence of everybody. So what do? So they both have G and they both have P. But the thing that makes it possible is that they both have their private secrets. They have things that they never tell anyone. So Alice selects at random some secret, and that's just something in the set from like 2 to like P minus 2. So P is huge. So this is a huge possibility, space of possibilities there. And Bob does the same thing. So he also, that's a terrible bracket. So Bob also picks one of these things at random, p minus 2 here. Okay, and they never reveal these secrets to anybody, not even each other. So what do? So this is sort of the private part. So here's the private key, but there's also a public key. So Alice creates A, which is G to the A mod P. And Bob creates B, which is G to the B mod P. And now Alice sends A to Bob. So you might ask, here's Alice sending A over a public communication channel, but this little A here is supposed to be forever secret. So what hard problem is it that prevents somebody in the public from being able to take this capital A and figuring out little a? It's the yeah, the discrete log problem. So she can publicly reveal this capital A because the discrete log problem is hard. So nobody can figure out what little a is. So Bob does the same thing. He sends Alice B, and for the same reason, nobody can figure out what little b is because nobody can solve the discrete log problem. But once they've done that exchange, look at what happens if you do. So Alice gets B, and she can raise B to A because she knows that. But that's just G to the B to the A, which is G to the BA. Okay, and over here, now that Bob knows big A, Bob can do big A to the little b, which is G to the A to the B, which is GAB. And so G to the BA is the same thing as G to the AB. And this is some big number that's some because G is a generator. This is some element of ZP star, and now Alice and Bob are the only people in the world that know it, and they can use that to start communicating privately using like AES or some other fast symmetric key cryptographic algorithm. So that's Diffie Hellman Key Exchange. It's kind of amazing. I think most people would say that this is impossible. We just did it.
I actually saw a really cool analogy for this a while back, that you can think of it like mixing paint colors. Like there's a public paint color, each of them have their own private paint color.
Oh,
And then
I've seen those diagrams, but I never got it until you explained it just now.
it's like I take the public paint color, mix it with my private paint color, send that over to Bob, and then he mixes it with his private paint color, and then we'll both end up with the same exact paint color because it has the same 3 paints in it.
I finally get the analogy. I never understood what people were saying about the paint. I guess I got distracted by the colors or something, but when you explain it verbally, I understand. I understand why people use that metaphor now.
Yeah, it makes it a lot easier to understand for me.
Yeah. Okay, so what is the public paint color? So
It,
there's
it could be any color. It's
yeah,
just something that I'm mixing my private paint color to get a unique color. Then I send that unique color over to him, and then since he's mixing it with his, and I'm mixing it with the one that he mixed with the public one, those 3 colors will always make the same color.
yeah, that's
But
cool.
only the public paint color is available to everyone, so no one's gonna know exactly what paint we picked.
Uh-huh. Wow, that's neat. Yeah, that makes sense. And that is kind of interesting too, because that's kind of a continuous valued version instead of a discrete version, because there's like
Mm-hmm.
yeah. Um, okay, so anybody have any questions on that? I guess I'll start taking the roll, and I'm going to stop the recording.